This video is for lesson 8-7 about inverse variation. In a previous chapter, we looked at direct variation, where two variables are related using this formula. Y is equal to k times x. As the value of x increases, y increases at a predictable rate, and that rate is given by the value of k. We're going to now look at inverse variation, in which the product of two variables is equal to a constant. As the value of x increases, the value of x would have to decrease in a predictable way in order to equal that constant number. Here's an example situation using inverse variation. When two pulleys are connected, as shown in this drawing, the one with the smaller diameter, this top one here, will revolve at a greater speed. If D1 and N1 are the diameter and the revolutions per minute of this top pulley, then the variables D2 and N2 can represent the diameter and revolutions per minute of that second pulley. In this situation, this relationship is true. The number of revolutions in the small pulley times its diameter has to be equal to the number of revolutions in the large pulley times its diameter. This is equivalent to this proportion. Look at the cross multiplication for this. It would be N1 times D1, that's what's right here, and that's equal to N2 times D2, and that's what's right here. You have seen this exact pulley system on a bicycle. This larger gear system here is the front sprocket where the pedals are. And this smaller gear system here is attached to the back wheel. If you've ever paid attention to what the sprockets and chain looks like, it has this look where the chain is narrowing to that back smaller pulley. The reason for that arrangement is as you pedal and make this first pulley turn, the back pulley, which is smaller, will turn faster. So you get more speed out of your pedaling. In our example situation, find the revolutions per minute of pulley number 2, that's this larger one, if D1 is 6, N1 is 150, and D2 is 10. To solve this problem, we use our basic setup, which is this proportion given right here, or if you prefer, this equation given right here. It truly does not matter. So N1 is 150. N2 is the thing we're asked for, the number of revolutions on pulley number 2. Then right here, this is D2, that's 10. And down here in the bottom, D1, that's 6. Now solve this, perhaps using cross multiplication. So 10 times N2 is equal to 150 times 6. Divide both sides by 10 to get an answer for N sub 2. This turns out to be 90. And the letter N was representing revolutions per minute, so it's RPMs. When pulley number 1, the smaller pulley, is turning at 150 RPMs, pulley number 2, the larger pulley, is turning at 90 RPMs. In that pulley situation, we say that N and D vary inversely as each other. Or another way to say that is, they're inversely proportional to each other. Here's the definition of inverse variation. Two numbers, let's call them X and Y, vary inversely when their product is equal to a constant. So X and Y are actual numbers, and the letter K will be an actual number when you're doing these problems. When you multiply X times Y, you always have to get the same answer. The graph of an inverse variation is a hyperbola, having foci equal distant from the origin, on the line y equals x or y equals negative x. The x-axis and y-axis are the asymptotes. So take a look at this first hyperbola. If you were to draw the line y equals x, so a diagonal line going right through the origin with a slope of up 1 over 1, the foci would be located on that line. For example, that might be one focus, and this might be the other focus. Remember that a hyperbola branch always is wrapping around the focus point. Notice as well how the x-axis is your asymptote line, because this branch here is getting closer and closer as you move left. And this branch right here is getting closer and closer to the x-axis as you go right. The y-axis is also an asymptote line. In this picture over here, it is the line y equals negative x that has the foci on it. So a downhill line, somewhere kind of right in there and right in there, would be your focus points. Here's another example. The force of attraction between two particles, each with a mass of 1 gram, varies inversely as the square of the distance between their centers. When the centers are 1 centimeter apart, the force of attraction is this many dynes. What is the force when they are 1 meter apart? So this question comes from physics, right? The study of gravity and particles. Let's create a model that fits the situation. As soon as we're told that the things vary inversely, we can get our model. We're told that the force of attraction, let's use the letter F for that, varies inversely with the square of the distance. For distance, let's choose the variable r. From that first sentence, we can write our model. Force times distance squared is equal to a constant. I'll call that constant k. Now, just like the problems about direct variation in an earlier chapter, we're going to discover the value of k by substituting in known numbers for f and d. That's going to come from this sentence here. When the distance is 1 centimeter apart, the force is this number. So for the letter F, fill in 6.67 times 10 to the negative 8. And for D, fill in 1 centimeter. Because it's d squared, we're going to square the 1. And that's equal to k. Now solve this. Timesing by 1 squared just gives you the same result. 6.67 times 10 to the negative 8 equals k. Then rewrite the formula now that we know the answer for k. And we're ready to answer the question, which is located right here. What is the force? So that means solve it for F when we know the distance is 1 meter. So leave the letter F and fill in a distance. Right here, though, you got to be really careful. The distance we filled in last time was 1 centimeter. And this one says 1 meter. So 1 meter is the same thing as 100 centimeters. So for the distance, I'm filling in 100, meaning 100 centimeters. And that's equal to the 6.67 times 10 to the negative 8. To solve for F, you would divide both sides by 100 squared. So take a calculator, you type that in, and you divide by 100 squared. The result is 6.67 times 10 to the negative 12. In the question, we're told that force is measured in dynes. So this question gave us one real-life application of inverse variation. There are many more applications of inverse variation, and they're not all from physics either. Let's try one more example for our notes. This time we don't have a real-life situation, we just have some numbers. It says determine the value of c. So to determine that coordinate right there, so that this statement is true, that y varies inversely as x squared. So as soon as we're told this, we can make our model. Y times x squared is equal to constant k. Then take known numbers for y and x to solve for k. Well, where are we going to get the known values of y and x? They're in this ordered pair. This is x, this is y. So for y, fill in 0.48. And for x, fill in 0.25 and square it. And that's equal to k. Now take a calculator and type this in. This makes 0.03 is equal to k. Now what do? You rewrite your model. And this time, fill in the value of k. Now what? How can we figure out the value of c? Well, what is the value of c? It is the x-coordinate of that ordered pair, and the 3 is the y-coordinate. So for the letter y, fill in 3. For the letter x, fill in c. Now solve this equation for c. What would you do first? Divide by 3 on both sides. You get c squared equals 0.01. Now what would you do? Square root. So you get c equals the positive and negative square root of 0.01. That makes plus or minus 0.1. Let's summarize the lesson. We looked at inverse variation, which follows the section about hyperbolas because if you graph in inverse variation, it makes a hyperbola. As the one variable gets larger, the other one gets smaller. Take a look at these graphs. At this dot right here, there's a very small x-coordinate, like x is 1, whereas y is like something like 10. But then as you start to move to the right, the x is getting bigger. Now it's 2, but the y got smaller. Now it's 5. The x doubled, the y got cut in half. So that inverse relationship makes this hyperbola drawing.